All right, let's start TensorFlow example. Okay, so it's a good idea to just search for an example and run that in your system. Make sure it's working. Familiarize the code. That's a very good way of learning. And from these learnings, next when we want to implement something ourselves, that time we can do it our own. Okay, so let's get started with this mnist example. In this Keras blog, there is this mnist example. It seems to be really nice. Okay, here you can see import NumPy, TensorFlow, import Keras, and from Keras import layers. We'll come to know why these are imported. And then there is prepare data. In this mnist, there are 10 classes, so num classes 10, and input shape. mnist images are 28 by 28, and grayscale images, so channel 1. If it is a color image, we will give input shape as 28, 23, I mean whatever, input height, width, and channels. Now, load the data, split it in between train and test. Okay, so here this Keras library itself is having a function called load data, which will download this data to your system if it is not already there in the Keras some cache folder. So from there we can get this xtrain, ytrain, xtest, and ytest. So these are our xy pairs. This is for training and this pair for testing. So it will automatically split whatever data available into this train and test. So let's say here we have some 100 this 28 by 28 by 1 images and 100 numbers here representing what are the corresponding numbers of each image. And let's say here some 10 images and corresponding 10 result or expected values. So but here practically some 60,000 or something like that is the number of images. We can check that by running the code, and then we are doing this conversion. So by default it will be uInt unsigned int 8 data type. So we need to convert it into float 32 for TensorFlow to use it for training. So we will convert this xtrain and xtest into floating type, and then we will divide it by 255 because, like we discussed earlier, we need to normalize the input. That's a good practice. So in order to normalize the image is having maximum value 255 only. So image values will be from 0 to 255. So that maximum value we are dividing so that the image will become in range of 0 to 1. And so we are doing that for xtest as well. And then we are expanding this dimension of xtrain by -1. Okay, so by default, this image will not be of size. It will be, there will not be this extra dimension. It will be just 28 by 28 image. So we need to add one more dimension so that it becomes 28 by 28 by 1 image. Because we have mentioned the input dimension as 28 by 28 by 1. So that's what is happening here. And then, okay, we can see the shape when we run. And yeah, here shape of 0 means number of images we can see here. Okay, so now another thing is the Y data. Y data we are converting to categorical. Means output Y is supposed to be whatever is the input image corresponding classification number, like 0 to 9. And for training, we need to make it as one-hot encoded. One-hot encoded in the sense, we know that here in this example, we have 10 output neurons. So one of these neuron will become high, like which are, like let's say here 4 is given, then this fourth neuron will become high value, others will be of low value. So like for training whatever this so we know that this we are expecting 4, we can't feed 4 directly, so we need to convert 4 into this binary representation. So 0 that corresponding binary representation of 4 will be given here, so 0 0, and fourth one not basically binary representation, we can say we need to say one hot encoded, like whichever is the index that is corresponding to that number, that index will be 1, others will be 0. So that is this one hot encoded format. So we need to convert our output number into one hot encoded vector. So this is 0 0 0, fourth one is 1, and rest everything is 0. That is the expected output, and that's what we need to feed here as the expected value in order to calculate the loss and then to calculate the readiness. So that is what is happening here. This white line will be one hot encoded. White test as well will be one hot encoded vector. Now building model. So whatever we have seen earlier, that's what is happening here. One input layer. So this is not having any computational part. It's just a placeholder for input, and its dimension is specified here as input shape, that 28 by 1. So this is where the model is created, and this is the input of model. So here we are using the sequential, where we can just stack together this model layers, and this model will be a connection of all these layers. Alright, then after input we have a 2D 32. So here we have 32 kernels of size 3 by 3, height and width 3. Such 32 kernels we are using for first level feature extraction. And activation is ReLU, like we discussed, that max of 0, 1. And then we have a max pool here, max pool 2D of size typical value itself 2 by 2. So after first convolution, we will do a max pooling. We will take the max of nearing 4 pixels and thereby reducing the height and width by 2. And then again another convolution, this time 64 kernels. So in a way this is a compensation for, like earlier there was 32 kernels and we did a max pool by half, mainly a compensation for this we can say. So half we have reduced in dimension, in spatial dimension we have reduced it by half. So we are increasing here the number of kernels, so that just kind of a compensation for that reduction. And here we are increasing in towards this other dimension, like here when we do max pool we are reducing width and height, but when we increase this convolution kernels we are increasing the depth, or basically number of channels in that layer. So we are extracting 64 kernel or 64 layer of information from this previous input. Again activation 6 ReLU, and again max pool, reducing size again by half, and this data is flattened and given to a dropout layer. So this flattening was for giving it into dense layer, and this dropout layer, basically what it does is it will randomly remove the values as per the fractions given. That many values will be just removed and replaced by 0, and that is what is fed to this dense layer. So this random removal will reduce the chance of overfitting on, let's say in the image there is a tiny dot, and because of that dot it is predicting it as something. When we do this dropout, there is a chance that dot features are not coming into the output, and based on rest of the information it will try to learn that that number is a 5 or 3. And then this final, so for that final dense layer, which will with the number of classes as output and activation as softmax. So softmax will make sure the value is in 0 to 1, and whichever class is belonging to, or whichever neuron belongs to output class, that will be near to 1, other neurons will be near to 0. So this list is created, given to the sequential function. It will create a model for us. All right. Yeah, sorry, sequential class. We are creating an object of that sequential class, and that will be our model. And that model, here we can, in TensorFlow, we can just type model.summary, and we can get the summary of the model. So we can see here input layer, and then first convolution, 20 is output. So this is, as the, we can read here, output shape, and this is the layer. So output shape of first convolution layer is 26, and why it is 26, not 28? Because we haven't done that padding here. So since we haven't done any padding, the dimension will start reducing because of lack of padding. So that's okay. And then we will do max pooling. Obviously, it is reduced by half. And then again, without padding, we are again convolving. So dimension again reduced to 11. And then again max pool reduced to half, 5. And then flattening. This is flattened. And then a dropout. So dropout, the dimension will not change. Just that randomly 50% of the values will be made to 0. And then given to dense, and the output of dense being 10. So that's how it is. We can see parameters. This many 34,826 parameters are there, out of which 34,826 all are trainable, and non-trainable parameters 0. And finally, training the model. In training model, like we discussed earlier, there is a batch size. So 128 images are taken together, and its output Y also taken together, 128 outputs and 128 images. This we will feed into network, and we'll do the we'll do the forward path, and then output will be noted. So all the 128 outputs will be compared to expected 128 outputs, and based on that the loss is calculated. So here we can see model.compile loss categorical cross entropy. So this is the loss. We will check that later. So categorical cross entropy is used as loss here, and then optimizer add them. This also we have touched upon. So there are different optimizers which will control like how the training proceeds, how the weights are adjusted, learning rate adjusted, such that we go into the maximum or least loss gradient. When we will follow the gradients, and when we will try to reach the global minimum of this problem statement. Whatever is our problem statement, that will have a global minimum, and there can be local minima also. So we'll touch upon that later. And then metrics. So here we can say, we can give what is the metric in it. Like we are calculating loss based on this function, and we want to showcase some accuracy, or let's say some kind of metric that we need to specify here. So in classification case, accuracy itself we can use as the metric. In some other case, we might have to use something else as a metric. And then finally, in Keras we have this fit function. So we can simply call model.fit of x train, y train batch size can be given epochs. Like how many epochs this entire, like let's say we have 100 images in our training set. So how many times these 100 images need to be visited? That is the number of epochs. And one epoch means we have visited all the images in our training set. And then validation split. So yeah, here we are giving only x train and y train. So in that case, if we give a validation split, it will automatically split 10% of this x train as validation, and that will not be used for training. That will be used for validation purpose only. And then we run this. We can see this log coming, epoch 1, how much time it took, what is the loss value in the first epoch, and corresponding accuracy. What is the accuracy at which initially, or maybe after one epoch, what is the accuracy. And here we can see, like in few epochs, 15 epochs, already shown it have reached 98.77 accuracy. Yeah, and finally, evaluate the train model. To evaluate, we can use this model.evaluate in Keras, and we just need to pass the x test, y test, where was equal to 0 if you don't want a lot of trains, and this will give us the score. And score of 0 is the loss, score of 1 is test accuracy. So 99.2% test accuracy after 15 epochs of training. Yeah, so next we will run this in our local in the terminal, and let's go through this.